Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So this is session 10. In today's session, we'll be working out some examples in three-phase AC circuits. So the first example is two wattmeters are used to measure the power input to a balanced circuit where the line voltage and line currents are VL and IL. Find the readings of the two wattmeters if power factor angle is 0 degree, 30 degree, 60 degree, 90 degree. Comment on observations. Now we know that in a three-phase circuit, the power consumed is measured by two wattmeters. One of the wattmeter reading will be VL IL cos 30 plus 5 and the other one will read VL IL cos 30 minus 5. These will be the wattmeter readings. So when power factor angle is 0, then W1 will be VLIL cos 30 plus 0. Power factor angle is 0 means power factor is 1, cos 0 is 1. So W1 is VLIL cos 30 plus 0. W2 is VLIL cos 30 minus 0. That means both are equal to VLIL cos 30. That means both the wattmeter readings are equal and both are positive. This is the observation from made when power factor angle is 0 or power factor is 1. Next, when power factor angle is equal to 30 degrees. So when power factor angle is 30, first wattmeter will read VLIL cos 30 plus 30 cos 60, that is cos 60 is half 0.5 VLIL. And W2 is VLIL cos 30 minus 30 or VLIL cos 0, that is VLIL. So when phi is 30 degree, power factor is cos 30, that is 0.866. At that time, both the wattmeter readings are positive and one wattmeter reading will be half of the other one. That is the observation made when power factor angle is 30 degrees. Both the readings are positive and one of the wattmeter readings will be half of the other one. Then next is when power factor angle is 60 degrees. When it is 60, first wattmeter reading VLIL cos 30 plus 5 or VLIL cos 90 is 0. Second one is VLIL cos 30 minus 60. VLIL cos minus 30, that is 0.866 VLIL. That means here the observation is, now the power factor is cos 60, that is 0.5. One wattmeter will read 0. That is the observation. Now above power factor angle 60 degree, one of the wattmeters will be negative only. Between 60 and 60 to 90, one of the wattmeter will give a negative reading. So far it was positive, 0 to 60, both the wattmeters will read positive. At 60, 1 wattmeter will read 0, and further perfect angle above 60 degree it will go negative. Wattmeter reading will be negative. So when phi is equal to 90 degree, W1 is VLIL cos 30 plus 90, that is minus half VLIL. W2 is VLIL cos 30 minus 90, VLIL cos minus 60, that is 0.5 VLIL. That means both the wattmeter readings will be equal, and one wattmeter will read negative. That means if we add the two, W1 plus W2, it is 0, because power factor angle is 90 degrees, so power factor is 0. At 0 power factor, real power will be 0. Real power consumption is 0. W1 plus W2 is equal to 0 when power factor is 0, or when power factor angle is 90 degrees. So these are some interesting observations. That is, when power factor is 1, both the readings, both the wattmeter readings will be equal and it will be the same. When it is 30 degree, both the wattmeter readings are positive and one is half of the other one. When power factor angle is 60 degree, then that is power factor is 0.5. One wattmeter will read 0. Then when power factor is 0 or power factor angle is 90, both the wattmeter readings will be equal, but one of the wattmeters will read a negative value, so that sum of the wattmeter readings is equal to 0. So negative reading means, so above power factor angle 60, one of the wattmeters will give a negative deflection. So we can get a positive deflection by interchanging the current coil terminals or voltage coil terminals. So it will read, when you interchange, say, voltage coil terminals, it will give a positive reading, but that value is taken as negative. Now next, a three-phase delta connected load draws 100 kilowatts. That is, power consumed by the complete delta circuit is 100 kilowatts, taking 200 ampere lagging current. So the line current is 200 ampere. It is lagging, which means the load is inductive. Find the parameters of each phase. What would be the power drawn if the connection is changed to star? Now the information given is the supply details 400 volt 50 hertz three-phase supply. The total power consumed by the delta connected load is 100 kilowatt. Line current is 200 ampere. Now from this information, that means VL is 400, IL is 200 ampere, then power is equal to 100 kilowatt. That means equation for power is root 3 VLIL cos phi. So from this, from the given information, we can find out the power factor. So root 3 into VL is 400, IL is 200, into cos phi is 100 kilowatt, that is 100 into 1000. So solving cos phi is equal to 0.72169, or phi is cos inverse 0.72, that is 43.8 degrees. Then here it is, the line current is given, which is 200 ampere. So it's a delta connected circuit. So phase current is equal to, so here I have marked the 200 ampere only in one line because it is the supply is balanced and the load is also balanced. All the line currents will be equal. IA, IB, IC, all will be equal. It's equal to 200 ampere. Then phase currents also will be equal. This is terminal A, B, C. So IAB, which is the current flowing here, IBC, this is IBC, then this is ICA, IBC, IAB. So all these currents are equal. So there's no need of specifying IAB, IBC, CA are equal to phase current only. So I'll just write phase current. So phase current is equal to, in a delta connection, phase current is equal to line current divided by root 3. So phase current is 200 by root 3, 115.47 ampere. That is the current in each phase. So now we know the phase voltage. Phase voltage is 400 volt. I'll mark one here. This is VAB. VAB, VBC, VCA all are same. Magnitude is equal to 400. So VAB, the voltage between these 2 points is 400 volts. And that means the voltage across impedance, say Z, I'll mark it as Z. The voltage across Z is 400 volt. Current through Z is I phase, that is 115.47 ampere. We can find the magnitude of the impedance. It will be Z phase. So impedance of any one phase is equal to voltage across it divided by current through it. Voltage is 400 volt, current is 115.47. Dividing will get 400 divided by 115.47, 3.464 ohm. That is the impedance of one phase. Now, we know the power factor, or we know the power factor angle. So now we got the magnitude of the impedance. This is Z phase. So R phase, that means the resistance of one phase. This is XL phase. This angle is the power factor angle, that is 43.8 degree. So what is the value of R phase? Z phase into cos phi, or cos 43.8. What is the value of XL phase? Z phase into sin 43.8. So we can find the resistance and reactance of each phase. R phase equal to Z phase into cos phi, that is 3.464 into 0.72169, that is 2.5 ohm. XL is equal to Z phase into sin phi. Z phase into Z phase is 3.464 into sin phi will give, into sin 43.8 will give you XL phase. It's equal to 2.39. So this is equal to 2.5 ohm. This is equal to 2.39 ohm. So L we can find out from this. XL value is 2.39 ohm. So L is equal to XL divided by 2 pi f. 2 pi f is 314. 2 into 3.14 into 50. Into 200. 100 into 3.14, 314. So XL divided by 2 pi f will give you 7.64 millihenry. So these are the values of parameters. That is, in each branch, the impedance has a resistance part 2.5 and a reactance value 2.39. Now the next part of the question is, if the connection is changed to star, the same impedances are connected in star and the same voltage is applied across it. Then the supply details remain the same. 400 volt 3 phase AC, 3 Hz AC, and impedance of each branch is Magnitude is 3.464, angle is 43.8. So Z1, Z2, Z3 all are the same. All these three impedances are the same and value 3.464 angle 43.8. So the same impedances are connected in star and the same voltage is applied across it. Now we have to find out the what would be the power consumed by the star connected load. Now here VAB is 400. This value is 400. So phase voltage is equal to, that is this voltage. This is the phase voltage between neutral and any one of the lines. So this value is V phase is equal to 400 divided by root 3 equal to 231. This magnitude of this voltage is 231 volts and magnitude of the impedance is 3.46. So we can find out the current. So phase voltage is 231, phase current is phase voltage divided by impedance of magnitude of the impedance of one phase. That is 231 divided by 3.464. It is 66.66 ampere. So the power consumed by the star connected load can be found out using one of these equations, 3I phase square into R phase, or root 3 VLIL cos phi. One of these equations. We'll try out both. So power consumed by any one impedance is I phase square into R phase. Likewise here also I phase square into R phase, I phase square into R phase. So adding 3 I phase square into R phase. That is 3 into phase value of current is 66.66 ampere into R phase is 2.5 ohm. 3 into 66.66 square into 2.5, it is 33.33 kilowatts. Or you can use the equation root 3 VLIL cos phi, root 3 into VL is 400, IL is, this is star connection, so phase current is equal to line current. Phase current, line current, both are equal in this case. So IL is also 66.66 into cos phi. Cos phi is 0.72, it is given here. So cos phi is 0.72. So by using this equation also we are getting the total power consumed by the circuit is 33.33 kilowatts. So in this delta connected circuit, we found out power factor first, then found the elements of the impedance, then connected in star, found out the total power consumption. Now next, three coils of impedances. 25 angle 30 is connected in star and is given at a 400 volt three-phase supply. Find the wattmeter readings. We have to assume that there are two wattmeters. One is connected here, another one here. M, L, C, V, M, L, C, V. Now we have to find out these wattmeter readings. So supply details 400 volt three-phase supply. Frequency is not given and not required. Impedance values are, it's balance the load only, that is 25 angle 30 in each phase. Now phase voltage we can find out. Line voltage is given, that is 400 volt. This voltage is 400 volt. So phase voltage, this value, it is VAN or VA. It is 400 by root 3 is 231 volt. So phase voltage is 231 volts. Impedance magnitude is 25. We can find out the current. So phase current is equal to phase voltage divided by phase impedance. So 231 divided by impedance of one phase is 25 ohms. 231 by 25 is 9.24 ampere. That is the phase current. This current is I phase is equal to 9.24 ampere. So phase current is equal to line current in this case. This is 9.24 ampere. So now perfect angle is 30 degrees. It is given in the question. So line voltage is given in the question. Using that, we found out the phase voltage. Line voltage divided by root 3. Line voltage is the voltage between two lines. Here I have marked VAB, which is 400 volts. So the voltage between neutral and the line, that is line to neutral or phase voltage, it is 400 divided by root 3 is 231 volt. So now we got the phase voltage and phase impedance. We can find out the phase current. It's equal to 230 phase voltage by phase impedance. 231 divided by 24. That is 9.24. Power factor angle is 30. So now we can find out the wattmeter readings. W1 is VLIL cos 30 plus 5 or 30 minus one of the wattmeter readings. One of the wattmeters will read VLIL cos 30 minus 5 and the other one will read 30 plus 5. So VLIL into, or I'll mark, take this as W1, this is W2, then this is W2 and W1. W1 is VLIL cos 30 plus 5. So VL is 400. IL is 9.24 because it's a star connection. Line current is equal to phase current into power factor angle is 30. 30 plus 30. The other one is same values of voltage and current. 400 into 9.24 into cos 30 minus 30 or cos it. So we are getting the readings as 3696 and 1848. So power factor angle is 30. So here W1 is half of W2. So it is when power factor angle is 30, one of the wattmeter readings will be half of the other one. So total power is sum of these two. 3696 plus 1848, that is 5545 watts. So total power also can be found. Total power can be found by using this equation also. Root 3 VLIL cos 5, root 3 into 400 into IL is 9.24 into cos 5, 5545. So the wattmeter readings are 3696 and 1848. Next. When three identical coils connected in delta is given a three-phase 400 volt 50 hertz supply. Line current is 10 ampere and the total power is 800 watts. Find the resistance and inductance of the coil. So in this question, line current is given 10 ampere. Three identical coils, that means the impedances are equal. Supply is balanced, load is also balanced. So all the currents, line currents, phase currents, all will be equal. Phase voltage is 400 volt. I'll mark VAB here. VAB is equal to 400 volts. Then line current is there, so we can find out phase current. This is I phase. This is A, B, C. This is IAB, IBC, ICA. IAB or I phase, which is equal to IBC, equal to ICA, all equal to 10 by root 3. Line current is 10 ampere, so phase current is 5.7735. It's equal to 10 by root 3. So now we know the phase current. Now the total power, as I told you, 3 I phase square R is equal to total power. I phase square into R plus I phase square into R plus I phase square into R. That is 3 I phase square R or R phase is equal to total power. We know the phase value of current, we know the total power, so we can find out the resistance per phase. So R phase is equal to total power 800 divided by 3 into I phase square. I phase is 5.7735. That is 7.989. Now next we can find out the impedance. We know the V phase. V phase is 400 volt. I phase is 5.7735. Divided, you will get the impedance of any one phase. Z phase you can find. So Z phase is V phase by A phase. Phase value of voltage is 400 volt. Phase current is 5.7735. So dividing, we will get 69.282. So we know the impedance. We know impedance per phase, resistance per phase. You can find the reactance per phase. R phase, XL phase, Z phase. So we know this. This is 7.989. Impedance per phase is 69.28 ohm. So this side is square root of 69.28 square minus 7.989 square is 68.81 ohm. So this is 68.81 ohm. So inductance, corresponding inductance is XL divided by 2 pi f or XL divided by 340.2192 Henry. That is the impedance. That is the value of inductance. So the resistance per phase is 7.989 and inductance per phase 0.2192 Henry. Next, a 400 volt three-phase motor has a full load output of 5 HP, efficiency 90%, power factor 0.8. Find the 2-wattmeter readings connected to on the input side. Okay, fine. W1, W2. Now, output is given, power factor is given, efficiency is given. Output is given, efficiency is given, we can find the input. Now, the output is given in HP, we have to convert to watts. Here, I think a metric HP is given, that is why 735.5, otherwise it is 746. Okay, let's take it as 735.5 for the time being. So output is 5 HP. So 5 into 735.5, 3677.5 watts. This is the output. So input is output divided by efficiency. Output divided by, so output by input is efficiency, or input is output by efficiency. Output is 3677.5. Efficiency is 90%. So divide with 0.9. It is 4086 watts. So input is 4086 watts. Your output is 3677.5. Electrical input and mechanical output. Now input is 4086. So input side we know the voltage, line voltage, that is 400 volt. Then cos phi we know it's given, that is 0.8. So we can find the line current. So root 3 VLIL cos phi is 4086. VL is 400. Cos phi is 0.8. So IL is 7.37. In all the lines, same current. So now we can find out the wattmeter readings because line current is known. W1 VLIL cos 30 plus 5. VL is 400. IL is 7.37. Cos 30 plus 5. 5 power factor is 0.8. So 36.8. So cos inverse 0.8. Power factor angle is cos inverse 0.8. That is 36.86 degrees. So first wattmeter reading 30 plus 5. 30 plus 36.86 is 66.86. So 400 into VL into IL into cos 30 plus 5 is 1158.5. Second wattmeter reading VLIL cos 30 minus 5. VL 400, IL 7.37, cos 30 minus 6.86. Cos minus 6, that is 2927 watts. So these are the wattmeter readings. Next. A three-phase 400 volt system is a delta connected load with set AB is 10 angle 0, BC is 10 angle 30, CA is 15 angle minus 30. So here the load is not balanced, it is unbalanced load. So the currents will be different. Now let's take VA, phase voltage. VA is equal to V phase angle 90. Whatever is the magnitude at an angle of 90. Assume a positive sequence VB, VC. These are phase voltages. The corresponding line voltages are VA, this is VAB, VA minus VB. This is VB minus VC. VC project backwards when the resultant. So this is VBC, VCA. So I'll write the equations for that. This I randomly have chosen. So VAB is, this is 400 volt system, 400 angle 120. VBC is 400 angle 0. And VCA is equal to 400 angle 240. So the phase voltages are actually not required. Line voltages are enough. I have chosen a positive sequence. So VAB taken as 400 angle 120. VBC is 400 angle 0. VCA is 400 angle 240. Any phasor you can take in the reference direction. So now these are the line voltages. Which are the phase voltages? So it's a delta connected load. So the current in this impedance, this is said AB, the impedance connected between terminals A and B. It's equal to. We know the voltage VAB. VAB is 400 angle 120. Said corresponding impedance between A and B is 10 angle 0. Therefore, IAB, the current from A to B, is equal to 400 angle 120 divided by 10 angle 0. That's 40 angle 120. Now, the current IBC. IBC is equal to, this is, I mark VAB. This is VAB. This is VBC. So IBC is equal to VBC divided by impedance of this branch, that is 10 angle 30. So IBC is equal to VBC by ZBC. VBC is 400 angle 0 divided by ZBC is 10 angle 30. So dividing, we'll get 40 angle minus 30. Then ICA. ICA is equal to VCA. I'll mark VCA. VCA divided by ZCA. So VCA is 400 angle 240. This is angle 120. This is angle 240. So all are 400 volt. So VCA is 400 angle 240 divided by ZCA is 15 angle minus 30, dividing you get 26.66 angle 270. So these are the phase currents. So first we have to choose the line voltage phases. So you can now I have taken VBC in the reference direction. You can take VAB also in the reference direction, or VCA in the reference direction. No. So VBC is equal to 400 angle 0. Then VAB is 400 angle 120 and VCA is 400 angle 240. If BC is here, then for a positive sequence, VAB will be at an angle of 120, VCA at an angle of 240. So mark the voltages here. Then IAB direction is required. So this is IAB from current from A to B. So VAB, this is the positive polarity. So current is like this. Then VBC, current is like this. VCA, current is like this. So IAB is equal to VAB divided by ZAB. That is 40 angle 120. IBC is VBC divided by ZBC. ICA is VCA divided by ZCA. So we got the phase currents. Now we have to find out the line currents. So line currents IA is equal to, have to apply Kirchhoff's law to this node, that is incoming currents are ICA and IA, outgoing current is IAB. So incoming current IA plus ICA is equal to IAB. So IA is equal to IAB minus ICA. So IA is equal to IAB minus ICA. IAB we know 40 angle 120. ICA is 26.66 angle 270. Subtract it. You have to convert both these terms to rectangular coordinates. Then simplify it, convert it back to polar. So we get 64.48 angle 108 degrees. Similarly, IB. IB apply Kirchhoff's law to this junction. Incoming currents are IB and ICA. Outgoing current is IBC. From that, IB is equal to BC minus IAB. IBC is 40 angle minus 30. IAB is 40 angle 120. Convert both to rectangular coordinates. Simplify. Convert back to polar. 77.78 angle minus 45. Likewise, you can find IC also. Now, phasor diagram. We have taken VBC, VAB, and VCA. Now, the currents are phase currents will mark. IAB is 40 angle 120. So, this is 40 angle 120. IBC is 40 angle minus 30. This is 30 degree. ICA is 26.66 angle 270. So, this angle will be 90 degree. So, positive it is 270. These are the phase currents. I'll mark about the angles, otherwise it will be too congested. Now we have to find out the line currents. IA is 64.48 angle 108. IA is IAB minus CA. So project to CA in the negative direction. This is minus ICA. Then find the resultant. Sorry. Complete the parallelogram, draw the diagonal. This is A. IA is equal to IAB minus ICA. ICA projected back. This is minus ICA and IA plus, no, IAB. This is IAB. IAB plus minus ICA, that will give you IA. So it's an angle of 108 degrees. This is 108 degrees. Then IB is IBC minus IAB. So BC minus AB, IAB is here, minus IAB is here. Complete the parallelogram, draw the diagonal, that is IB. So it's an angle of 45 degrees, minus 45. Magnitude is 77.28 at an angle of 45 degrees. Then IC is ICA minus BC. CA minus BC. That is BC projected back. ICA. This is the resultant. That is 35.27 at an angle of minus 169. So this angle is 169 degrees. Magnitude is 35.27. That is the phasor diagram. So that's all for today's session. If you like the video, please share it among your friends, and thanks for watching.